Yes.
Okay. Today is lecture number 15. This is the last lecture of the chapter of superconductivity. We are going to continue discussing microscopic theory of superconductivity. You remember that on Monday you will have a tutorial number 4, when with Andrei you will use the equations which I'm going to derive today for computing thermodynamics of superconductors. But today, as I said, I'm about to discuss Bardian-Cooper-Schrieffer theory of superconductivity. So it's lecture number 15. The title is Microscopic Theory of Superconductivity, Part 2. And be more precise, it's Bardian, Cooper, Schrieffer, which is abbreviated as BCS, and this is very common abbreviation theory. Let's briefly recapitulate what we have learned the day before yesterday. So we discussed the situation when two electrons in the very small, very narrow skin in the vicinity of Fermi surface, so this is PF, interact through the electron-phonon interaction. And we have found that as long as the condition, so this is K2, K1, as long as we consider the center of momentum of the Cooper pair, which is K1 plus K2 half modulus is smaller compared to cup critical, we see that two electrons form a Cooper pair because of the attractive interaction mediated by electron-phonon interaction. We discussed that the wave function of the two electrons, R1, R2, which describes the spin degree of freedom and orbital degrees of freedom, sigma 1, sigma 2, times chi, sigma 1, sigma 2. The psi is responsible for the orbital degrees of freedom, and chi is responsible for the spin degrees of freedom. We consider this duration without magnetic field, and we said that according to the very general theorem of quantum mechanics, the wave function of the ground state should not have nodes. So this wave function, this is what is called S pairing, no nodes. And since this function doesn't have nodes, it should be symmetric. R1, R2 is equal to plus psi R2, R1. Otherwise, you will have a point where the wave function is equal to 0 and change sign. However, we know that from the Pauli principle, the wave function phi, sigma 1, sigma 2, R1, R2, should be antisymmetric with a full replacement of all indexes. So this is psi R2, R1, and the sign is minus, times chi, sigma 2, sigma 1. This is a Pauli principle. From this, we concluded that chi, sigma 1, sigma 2 is equal to chi, sigma 2, sigma 1, and the Cooper pair is singlet. Namely, if we have two spinors, then explicitly chi sigma 1, sigma 2 in the basis up down can be written as down minus down up, normalizing factor square root of 2. So indeed, in explicit form, you see that chi up down is equal to minus chi down up. So the Cooper pair is singlet. And then we said that we can approximate our interaction such a way. So let me write down now the Hamiltonian. H is equal to H naught plus 1/2 sum over K1, K2, Q, sigma 1, sigma 2, V, Q, A dagger K1 minus Q, sigma 1, A dagger K2 plus Q, sigma 2, A sigma 2, K2 sigma 2, A K1 sigma 1. So we said that considering very vicinity of the thermal surface, so the width of this nutshell is twice the Debye frequency, where the phonons result in attraction between electrons, we can say that V, you see that it's K1 minus K2. This is the conservation law, is equal to minus V naught if epsilon K1 minus epsilon K2 is smaller than H of the dim, and 0 others. So as a result, H naught is a kinetic energy, sum over K sigma, epsilon K, A K sigma dagger, A K sigma. As a result, we can replace this initial model by approximate model, which is BCS model, where I'm saying that H interaction, BCS, is equal to, first of all, we have attraction. So this is minus modulus V naught. Then I take a summation and I will denote it as a prime, and I will be summing over state K1 and K2. And I'm saying that I'm considering Cooper pair A K2 minus K2 A K2. Let me see that in my notes I use the same notation. No, I would prefer to write 2 here and 1 there. K2 minus K2, K1, K1, and I also said that I'm considering the singlet Cooper pair. Therefore, I put up down and down up. And since I have two possibilities, I can put up down or down up, and the same here. And after I commute this variable, it will double me the identical term. Therefore, I abandon factor 1/2. So this is the model which I'm going to consider. And you see, this model is approximation to the full model because, first of all, I assume this particular type of the interaction, and I denote it by putting prime on the index of summation. Prime assumes that I'm only summing over the states in the vicinity of the thermal surface, defined by this condition. And then, in addition, I assume that the Cooper pair is considered at 0 momentum of center of mass, and the Cooper pair is singlet. So, You may ask me why phonons come in the mind of theorists, why people start to look about phonons. There was actually experimental indication that the temperature of known superconductors depends on the isotope you use. Namely, you can use system with different isotopes. You know, sometimes you have this option to take material with a different isotopic content, and people realized that the critical temperature inversely proportional to the square root of mass of the isotope. And then it immediately came to the mind that since Debye frequency is, say, some modulus stiffness, I will put it K divided by M, since the Debye frequency satisfies this criteria, people start to think that maybe phonons are involved, and therefore this treatment of phonons and discovery that phonons can mediate the pairing being resulting in attractive interaction for small energy transfer defined by this condition. Okay, I have formulated the model, and now I'm going to proceed with calculations. So this is the goal of my today lecture. You should have understanding. I'm going to tell you within 1 hour and a half the result of the work, which 20 years after, even less than 20 years after its publication, actually was awarded by the Nobel Prize. So in 1 hour and a half, we will go through all calculations, and at the end of the lecture, arrive at equation, which is known as BCS equation, which will be in the core of the microscopic theory of superconductivity. Again and again, microscopic, because I'm considering some particular mechanism associated with electron-phonon interaction. I introduce the strength of electron-phonon interaction, and at the end of the calculation, we will see that equation will contain microscopic parameter of your material, namely strength of electron-phonon interaction and the density of states at the Fermi level. So it is material specific, and knowing these parameters, one can describe the behavior of spectrum, instability of your ground state, and actually much more than that. You will see how to apply this theory on tutorial Monday, but we are about to derive the equation. Good. And as usual, deriving means that we are going to diagonalize the Hamiltonian. And in order to diagonalize the Hamiltonian, we will use the Bogoliubov transformation, which I introduced to you when we discussed Bose-Einstein condensate. So it was introduced for bosonic system. Now we are going to do the same for the fermionic system. And in order to introduce new variables, so the logic is pretty the same. I introduce new quasi-particles, for which I would like to write the new Hamiltonian just in the form of H naught, with some new dispersion, new energy spectrum, and new quasi-particles B, which of course should satisfy the same commutational relations as my old quasi-particles, in which representation the Hamiltonian is not yet diagonal. So you see, since I'm dealing with a singlet state, I need to mix the state with the spin up and down and creation and annihilation operator. Therefore, I'm writing this mixture, the new quasi-particles B, bk down is equal to uk ak down plus vk b minus k dagger up. So you see that contrast to bosons, which did not have spin degrees of freedom, here I need to mix fermionic state with a k and minus k, sorry, it's A, of course, and spin index up and down. So if I complex conjugate, and by complex conjugating, I take the same assumption that u minus k is equal to uk, d minus k is equal to ek, and uk star complex conjugated is equal to uk, and vk star is equal to vk. So the coefficients u and v, which I introduced here, this is uv transformation, or Boголюбов transformation. I make this conjecture that coefficients behave on this way, and after proceeding with calculations, I will see if my conjecture is correct or not. So therefore, now I can conjugate b dagger k down is equal to uk a dagger k down plus bk a minus k up. Again, I'm mixing states with a k and minus k and up and down. Then b k up is equal to uk a k up minus vk a minus k dagger down. And therefore, vk dagger up is equal to uk a dagger k up minus vk a minus k down. In a short form, I can write it down. So, of course, I need only pair of the states. I can write it down as bk dagger up, b minus k down is equal to uk bk minus vk uk a dagger k up, a minus k down. Of course, you can write down the second pair very easily, but for me it's sufficient to write it in one. Just write it one. Sorry, it's minus and plus. bk up, I have a minus here. So, as usual, I call this matrix and denote it by the letter U capital. Then, I need to do the exercise. Namely, I'm saying that the commutation relation for my old, this is old variables, these are new variables. I know that my old variables satisfy commutation relations AK sigma, AK dagger sigma. These are commutation relations with a sign plus, sometimes denoted with a figure bracket, AK sigma dagger, which is by definition is AK sigma dagger plus AK sigma dagger AK sigma is equal to 1. If the momentum indices k here and k there are not coinciding, or spin indexes here and there are not coinciding, I have a 0. So this is the only situation when I have 1, when I have a k, sigma, and so on and so forth. This is given to me because I know that the Hamiltonian, this one, is written in terms of the fermion. In order to guarantee that my new variables satisfy the same commutation relations, bk sigma dagger plus is equal to 1, I need to rewrite my new variables in terms of old variables. This is what I did. Plug it in to the commutation relations. This is what I did for the bosons. And then I will find a condition on the elements of matrix U in very similar way as I did it for bosons. The condition tells me that determinant u, which is uk squared plus vk squared, should be equal to 1. Please do this exercise. This exercise is for you. Plug in these new variables in terms of old variables, commute them, and in order to guarantee that new variables are also subject to Fermi-Dirac statistics, you derive this condition for the matrix U. Good. I can therefore compute the inverse matrix. U minus 1 is equal to uk vk minus vk uk. And you see that the matrix U minus 1 is equal to U transposed. So this is not only unitary transformation, but also orthogonal transformation. Orthogonal means that I can have a freedom to choose these coefficients, real, and matrix U is real. Orthogonal transformation means that this is a rotation. Without losing generality, using this condition, I can say that UK is a cosine of angle theta k, and VK is sine angle theta k. So my UV transformation for fermionic system is orthogonal transformation, which is a rotation in the Fock space. The Fock space itself, as I said, is compact. This is because of the Pauli principle. And as a result, my rotation is a rotation of on a compact manifold. In particular, here, this is a rotation on a sphere. And this is again a difference between UV transformation for bosonic system, where, if you remember well, I parameterized U and V by cosinus hyperbolicus and sinus hyperbolicus, cosh and sinh. Here, these are just trigonometric functions. Good. Since I know my inverse matrix, I can write down my old variables expressed in terms of new variables, plug it into the Hamiltonian, and write down my approximate Hamiltonian in terms of new variables B. This is what I'm going to do during next minutes. But before doing that, let me rewrite the variables A in terms of variables B. Using that A k up diagonal as A minus k down is equal to UK VK minus VK UK VK diagonal up V minus k down. I'm writing explicitly connections. So A k diagonal up is equal to UK VK diagonal up plus VK V minus k down. The complex conjugated is AK up is equal to UK VK up plus VK V minus k diagonal down. Then for the system down, AK down minus k down is equal to minus VK VK diagonal up plus UK V minus k down. And A minus k diagonal down is equal to minus VK VK up plus UK V minus k diagonal down. And then of course I can replace k to minus k in order to get all possible variants for the operators A, which I need for the Hamiltonian. Okay? No questions so far? So I will keep model, I will keep transformation, and now I will dwell into the calculations. I will use, first of all, I will come from the canonical Hamiltonian to grand canonical Hamiltonian, which is H minus mu n. So n is sum over k sigma a k dagger sigma a k sigma. I use the fact that chemical potential is at temperature equal to 0 is thermal energy. And I use the spectrum. I will take the shorthand notation, psi k is equal to epsilon k minus mu. So basically, I do what I did always in the Fermi liquid theory. I shifted everything by the chemical potential. I know that in this case, the spectrum in the vicinity of the Fermi surface is linear, and the excitations are electrons and holes. So these are my shorthand notation. So then H naught, which is H naught minus mu n, is equal to sum over k psi k a dagger k sigma a k sigma. Now I write down apparatus A in terms of apparatus B, and therefore this is sum over k psi k. First, A dagger k up, A k up, U k B k dagger up, plus V k B minus k down, times U k B k up, plus V k B minus k dagger down. So this is the term up, up. Now the same term down, down, plus UK BK dagger down minus BK B minus K up times UK BK down minus VK B minus K dagger up. This is H naught. Now I open the brackets and collect terms in front of the diagonal and off diagonal terms. So this is sum over k, psi k. So UK square, BK dagger up, BK up, plus BK dagger down, BK down. UK square, BK dagger up, BK up, plus BK dagger down, BK down. Plus, minus, plus VK square. B minus K down, B minus K dagger down, B minus K down, B minus K dagger down, plus B minus K up, B minus K dagger up. In principle, I can replace K to minus K because I have a summation. Psi is even function and Vk is even function as well. Now, I have terms which are off diagonal, plus UK Vk, and I have all terms BK dagger, B, B, BK dagger, BB. So I will just write it schematically, B dagger plus BB, because you will see that these terms are not going to be important for me. Contrast to the diagonalization in bosonic system, where from very beginning I had a quadratic form and need to bring it to the diagonal form, here I still have a 4 fermionic terms. Therefore, instead of dealing with Hamiltonian, I'm going to deal with the expectation value of the Hamiltonian, namely energy. If I denote E naught as expectation value of the Hamiltonian H naught, I see that I need to take following averaging. As a bracket, you may think that I'm dealing with ground state. If I'm at 0 temperature, and I'm dealing with the Gibbs states if I'm at final temperature. For simplicity, let's assume that this averaging means the averaging with respect to the ground state. So, in the averaging of the operators B, K, sigma, dagger, B, K, sigma, I get N, K, sigma. The averaging B, K, sigma, B, K, sigma, dagger gives me 1 minus N, K, sigma, right? But the averaging of two creation or two annihilation operators gives me 0. Therefore, after averaging, this term will go. So the epsilon node is then equal to sum over K psi K. Here I have UK squared minus VK squared NK up plus NK down and minus 2 times plus 2 times VK squared. Okay, so this is what concerns the free part of the Hamiltonian related to the kinetic energy. Let me do the same for computing the interaction part. I will rewrite my Hamiltonian written here in terms of the new variables, and then I will take the expectation value of this part of the Hamiltonian. Good.
I'm sorry. Can I have a question?
Question?
Yeah. So you're averaging in the new ground state, right? Not in the Fermi liquid ground state.
Yes, yes. Well, but I defined it. M, the Fermi distribution function, is a Fermi distribution function of new quasi-particles.
Okay.
But my hope is that I will rewrite my Hamiltonian in terms of non-interacting quasi-particles. Therefore, the question is, what is the spectrum which is contained in the Fermi distribution function? But anything what I say is just I have a fermions and that's it. Of course, I'm taking average with respect to new ground state.
Okay.
But my quasi-particles are fermions.
Mm-hmm.
Okay. The interacting part of the Hamiltonian before I take average. Here I don't need to write a curly H because I already incorporated chemical potential in the H node. So this is minus modulus V node sigma prime K1 K2. So AK2 up, A minus K2 diagonal down. So first of all, I open the bracket. UK2 BK2 dagger up plus VK2 B minus K2 dagger down times UK2 B minus K2 dagger down minus VK2 BK2 up. These are these two terms. Times UK1 B minus K1 down minus VK1 BK1 dagger up times UK1 BK1 up plus VK1 B minus K1 dagger down. So I have a product of 4 terms. So let me again.
Sorry?
Yes? Yes?
Can you help me on the expression you wrote on the energy note? I cannot read it clearly.
Which one you cannot read? This
In
one?
note. Yes, yes.
I will rewrite it again.
Okay.
Let me finish with these calculations, and then I will erase everything which is related to Hamiltonian. I will not need it anymore, and then I will rewrite both E node and E interaction, because we will be working with this for maybe 10-15 minutes. Okay?
Okay.
Good. So this is minus V node sum prime over K2. So I have diagonal term, which is minus UK2 VK2 times B dagger K2 up, B dagger minus, B K2 up. I'm writing diagonal term. Minus B K minus K2 down, B minus K2 dagger down. Plus terms which are proportional to B dagger, and BB. I will write B dagger plus OB times sum over K1. Again, I open the bracket. I have minus UK1 VK1 here times BK1 diagonal up, BK1 up, minus B minus K1 down, B minus K1 diagonal down, and again plus O B dagger plus O B. So when I take averaging, now I don't need Hamiltonian anymore. When I take averaging with respect to ground state, this term are gone. However, I see that the terms in the brackets, namely this one and this one, are identical. They are coming in the same sum. So what I will write as the sum square. H interaction is equal to minus V node. And now this is a sum prime square. And what stays in the sum is UK VK times N times 1 minus NK up minus NK down. So I incorporated this sign minus, and minus will give me plus. Therefore, it comes with minus, and after I use this averaging, I got what I got. And this is averaging. I denote it as A interaction. And for Peluche, I rewrite E node, which is sum over K sine K UK square minus VK square NK up plus NK down plus 2VK square. So, E node and E interaction. Good. Okay. This is very important for me, and now I can erase everything else. I don't need these parts of the Hamiltonian, and I don't need connection between old and new variables. And you see, after taking average, I'm not dealing with the Hamiltonian anymore, but I'm dealing with energies, where energies depend on coefficients u and v. U and v are connected through the determinant. So I have UK squared plus VK squared is equal to 1. It comes from the determinant. Now, what I'm going to do, I'm going to minimize my energy. So the total energy is equal to E node plus E interaction. And I'm going to find delta E total with respect to real coefficient UK and say that this is equal to 0. So I'm minimizing my energy of the ground state with respect to coefficient U, because U and V are connected. It will give me a possibility to find a second equation, second nonlinear equation for U and V, which I solve, find this UV coefficient explicitly, and obtain the BCS equation. So, how to take the variation of the total energy with respect to coefficient U and V? This is the very same as I take a derivative. This is the very same as I did for the Ginzburg-Landau functional. I take UK square. I replace it by UK plus delta UK square, which is UK square minus plus 2 UK delta UK plus delta UK square. And therefore, I compute energy total at UK plus delta UK. I subtract energy total at UK, and I divide it by delta UK. And this is precisely what is delta total over delta UK. But UK and VK coefficients are connected. Therefore, whenever it is possible, in order to take this derivative, I need to express V in terms of V. So VK squared is equal to 1 minus UK squared, and VK is equal to plus minus square root over 1 minus UK squared. For the purposes of my derivation, I will fix sign of the square root. I will take the sign plus. You repeat these derivations, taking the sign minus, and you will obtain the very same equations at the end of the day. But by taking here the plus, I'm assuming if I took plus, if plus, it means that UK times VK is positive. Here. If I will take minus, I will need to follow everywhere in the steps of derivation that the condition is different, namely that UK times VK is negative. Good. So here, UK minus VK is 2 times UK squared minus 1. Good. So let me take this derivative step by step. I start with epsilon naught. So epsilon naught is sum over k psi k 2 UK square minus 1 times nk up plus nk down plus 2 minus 2 UK squared. Okay, good. It is equal to sum over k sine k 2 UK squared nk up plus nk down minus 1 plus 2 minus nk up minus nk down. I just rewrite identically this term and this term. And since I'm taking the variation with respect to u, I'm only interested in this term. So delta E naught over delta UK. So I need this term. Since I'm varying, my energy is functional because it depends on UK through the sum or integral. Since I'm taking derivative or functional derivative with respect to UK, I pick up particular k. Therefore, I drop sum over k. So this is 4 times. 2 comes from here. 2 comes from this. It's 4 times psi k. And I have UK, and I have nk up plus nk down minus 1. So this is the first part of my functional derivative. Let me rewrite it here. I hope that you remember how we take the functional derivative of variation by deriving Ginsburg-Landau. It is pretty the same, except for Ginsburg-Landau equation, I took a derivative, functional derivative, or derivative of the function, assuming that my order parameter is complex. Here, I'm taking derivative with respect to u, v coefficients under this connection, and I assume that both coefficients are real. So delta E node over delta UK is equal to 4 sine K UK n K up plus n K down minus 1. Good. Now I need to take a derivative of the interacting part. And U and V are sitting here. Before taking the derivative, let me do one more exercise. Namely, I will need to take delta UK VK over delta UK. Let me do this exercise. I'm taking the variation of the product. This is very similar to taking derivative of the product. So this is delta UK over delta UK times VK plus UK delta VK over delta UK. The first term, of course, gives me VK. And VK, you remember, is square root 1 minus UK squared. I need to express everything in terms of the UK. Plus UK. Now, this is a standard derivative over V. I remind you that V is considered to be plus square root 1 minus UK squared. So therefore, this derivative, first I take a derivative of square root 2 square root 1 minus UK squared. And I now take a derivative of the argument. This is minus 2 UK. 2 and 2 cancels out. I multiply the square roots and I get 1 minus 2 UK squared divided by square root 1 minus UK squared. Good. This is what I will need soon. Okay. Delta E interacting with respect to delta UK. So first of all, I am differentiating some power laws. First of all, I need to take a derivative associated with a square. So this is then minus V node 2 times modulus V node sum over K prime UK VK 1 minus NK minus up NK down. So this is, I took derivative of the product of two sums. Now I need to take a derivative of the functional. It gives me delta UK VK over delta UK times 1 minus NK up minus NK down. You see that what I have here is again some functional of UK and VK, and let me denote it, introduce a notation, and call it delta. So what I have then is minus 2 times delta, where delta is this one, and I plug in what I obtained before. 1 minus 2 UK squared divided by square root of 1 minus UK squared times 1 minus NK up minus NK down. So delta E interacting over delta UK is equal to minus 2 delta (1 minus 2 UK squared divided by square root 1 minus uk squared, 1 minus nk up minus nk down. So now I put things together. Okay? Delta E tot over delta UK is equal to. Let me first take the multiplier 1 minus nk up minus nk down, because both brackets are proportional to it. From the first term, I have minus 4 psi k uk. From the second term, I have minus 2 delta 1 minus 2 uk squared divided by square root of 1 minus uk squared, and this altogether should be equal to 0. Therefore, I request that this bracket is equal to 0. So I have equation 4 times psi k uk is equal to delta 2 uk square minus 1 divided by square root 1 minus uk square. Or if I recall that this is vk, this is 4 times psi k uk vk is equal to, I cancel by 2, 2 times is equal to delta 2 uk squared minus 1. I should remember that uk and vk is positive because I took the branch of the square root with sign plus. What we have here is uk square minus vk square. Therefore, if I take the square root with a sign plus, it immediately means that uk is bigger than vk. So let's remember it. So uk vk positive means that uk is bigger than vk. Because uk square minus vk square is also positive. Good. So I have two equations. Equation number 1 and equation number 2. Therefore, I can find u and v coefficient by solving these two equations. This is what I'm going to do next. So how much time do I have? Enough. Okay, in order to do it, I will take square and again re-express of the second equation and re-express v in terms of u. 4 psi k squared uk squared 1 minus uk squared is equal to delta squared 4 uk to the 4 minus 4 uk squared plus 1. I have a big quadratic equation. I will collect in terms about in front of the uk 4. 4 uk to the 4. I have psi k squared plus delta squared minus 4 uk squared. Again, I have psi k squared plus delta squared plus delta squared is equal to 0. Or uk to the 4 minus uk squared plus delta squared divided by 4 times psi k squared plus delta square is equal to 0. I have a big quadratic equation, therefore I'm writing the solution of big quadratic equation. Basically, I do everything for you in front of the board. This piece of paper, I never look at it. I only look to check that I didn't make a simple mistake deriving the black board. So, UK squared is equal to 1/2 plus 1/2. 1 plus minus square root over 1 minus delta square of psi k square plus delta square. Therefore, vk squared, which is 1 minus vk squared, is equal to 1/2 1 minus plus square root of psi k, 1 minus delta square over psi k square plus delta. As I said, this condition tells me that u is bigger than v, therefore I will take sign plus here and sign minus there. Let me denote e k as a square root over psi k square plus delta square. Just a notation. Nothing more than notation. Therefore, uk squared is 1/2 1 plus psi k divided by ek, and this is 1/2 1 minus psi k divided by ek. By the way, you see from construction that all my assumptions made as a conjecture are correct. Namely, uk and vk are real functions, and uk and vk are even functions of k. So I didn't come into contradiction to any of my initial assumptions. So then uk squared vk squared is equal to product of this 1/4 1 minus psi k squared divided by ek squared. So this is delta squared over 4 ek squared, and uk squared minus vk squared is equal to psi k divided by ek. So I have 1/2 and 1/2. That's it. Good. Now I didn't make any mistake. I can proceed to skip this. Now I need two things. First of all, let me restore my notation of the delta. So delta. I define the delta as modulus we know, sum prime over k, uk bk, 1 minus nk up minus nk down. So uk vk from here, you remember that this is positive, is equal to delta divided by 2ek. Then, if I don't have magnetic field, then nk up is equal to nk down. So I have equation that delta is equal to modulus, you know, sum prime over k, delta divided by 2 square root over delta square plus psi k squared, 1 minus 2 n. And of course, I can cancel out delta in the right hand side and in the left hand side. Good. Now, let me look what kind of spectrum is in the Fermi distribution function here. So therefore, I'm asking the question, what is the dispersion of my quasi-particles? Because by deriving these two nonlinear equations, one is coming from the determinant of matrix U equal to 1. It follows from the request to have the same commutation relations for my new variables as for my old variables. The second one comes from the minimization of the function of energy. Let me find out what is Ek, where introduce notation psi k squared plus delta squared. What is Ek? Okay, we follow the Fermi liquid theory basis, and by the definition, if we are interested in the dispersion of new fermions, which I denote B, I will call it E tilde k up. It is the variation of the total energy with respect to the distribution function n k up. So therefore now I need to take the variance of my energy, but not with respect to u and v coefficients, but with respect to the Fermi distribution function. And I recall you that epsilon naught was equal to sum over k psi k u k square minus v k square n k up plus n k down plus 2vk squared. Therefore, this is delta E naught over delta n k up plus delta E interaction with respect to delta n k up. I can take the same derivative with respect to n k down because in the absence of magnetic field, there is no difference. But for the purpose of the illustration on the blackboard, I took n k up. So, therefore, the first term can be easily obtained. The energy depends linearly. So this is uk squared minus vk squared times psi k. This is the first term. The second term, I recall you that E interaction was equal to minus v naught sum over k prime uk vk 1 minus n k up minus n k down square. Therefore, the variance with respect to n k up of the interaction gives me first minus 2 v naught sigma prime uk vk 1 minus n k up minus n k down. But this is delta. If you remember, now I need to multiply it by minus uk vk, and that's it. So, what I have together, uk squared minus yek squared is equal to psi k over ek. So I have a psi k squared over ek minus and minus gives me plus 2 delta. And times uk vk is delta over ek. Delta over 2 ek. 2 is cancelled out. So I have a psi k squared plus delta squared divided by Ek. So I have Ek. So my new dependence of the energy of the quasi-particles on the wave vector is given by this equation. Therefore, the meaning of the Ek is a new spectrum of the new quasi-particles. This is spectrum. Therefore, here, Nk is equal to the Fermi distribution function e to the power square root of xi k squared plus delta square of temperature plus 1. So I have a closed equation for the gap. You see that delta is gap in the excitation spectrum, and my equation identifies this gap. Before I canceled out delta in the left-hand side and the right-hand side, I would like to draw your attention to the fact that initial equation allows also trivial solution. If delta is equal to 0 in the right-hand side and the left-hand side, I have identity. However, if delta is non-zero, I'm getting a new non-trivial solution of this equation. And this is precisely what happens with the order parameter. Order parameter is equal to 0 at the temperatures greater than critical temperature and non-zero for the temperatures above the critical temperature. So now let me come back to the discussion of spectrum. And then we are going back to equations and derive some interesting properties. So we had Fermi liquid. So this is epsilon k minus mu, which is xi k, as a function of k. This is a Fermi model. We said that we can reflect this parabola and we can write down this branch. We are saying that these excitations are electrons and these excitations are holes. Now, my new spectrum is square root. So it behaves this way, and at Kf, where psi equal to 0, I have a delta. So the spectrum of my excitations is gapped, and as you will see on the tutorial on Monday, this gap is one-to-one related to Ginzburg-Landau order parameter, which is the wave function of the Cooper pair. Let's now find what this gap is equal to at 0 temperature, what is the critical temperature, and how the order parameter, which is delta, depends on the temperature. So my equations now actually describe full range of the temperatures, not necessarily temperature close to the temperature of superconducting transition, because if I consider it ground state, by the way, in the ground state, there are no occupied states, there is a gap. The Fermi distribution function at the ground state is equal to 0. However, if you at finite temperatures, you plug in the Fermi distribution function, and as a result, this equation defines function delta as the function of temperature. Let's now analyze this behavior qualitatively. Okay? However, the meaning of this order parameter, as I said, is the gap in the spectrum. First of all, zero temperature. If temperature equal to 0, as I said, Nk is equal to 0. Then the equation reads 1 is equal to 1/2 modulus V naught sum prime over K1 divided by square root over psi K square plus delta square. So 1/2 comes out of here. The Fermi distribution function is 0. This is BCS equation at temperature equal to 0. I can replace summation by integration. So let's consider right-hand side is equal to 1/2 modulus V naught. I'm integrating from minus omega d to omega d. You remember I have a model where the interaction is defined in the nutshell of the width 2 omega d. This is a Fermi surface. As usual, I write density of states, mu psi, d psi, divided by square root of psi square plus delta square. This is how I came from summation over k sigma prime to the integration. And since this density of states is defined for spinful situation, for spin up and spin down, and here I fixed the spin projection, I will write down 1/2. Good. So we know that the Fermi energy is much larger than Debye frequency. Typical Debye frequency is of the order of room temperature, 200-300 kelvins. The Fermi energy is 10,000 kelvins or larger. Therefore, without losing generality, I can took out the density of state in front and put it in front of integral. So I have 1/2 V naught times density of states at the Fermi level. I have two integrals from 0 to omega d and from minus omega d to 0. They are identical. Therefore, instead of writing integral from minus omega d to omega d, d psi square root over psi squared plus delta squared. So I took two integrals, and therefore I cancel out the factor 1/2. So this integral can be computed using a table. You can make hyperbolic substitution. You can compute it yourself. I'm not going to do it in the blackboard. I will write the answer. This is 1/2 V naught density of states at the Fermi level, and this is so-called long logarithm. This is logarithm of omega d plus on the upper limit square root over omega d square plus delta square divided by delta. Okay, and in the left-hand side we have 1. Let me denote this as a coupling constant G. So I'm saying that G is 1/2 modulus V naught times density of states at the Fermi level. And let me assume for the moment that delta is itself much smaller than the Debye frequency. Okay, then we can easily resolve this equation, and we get that delta is equal to 2 omega d e to the power 1 minus over g. So this is 2 times Debye frequency exponent as minus 2 divided by V naught density of states at the Fermi level. If you look at my derivation of the Cooper pairing problem, you will see that delta is exactly equal to the difference of the energy of the binding energy and 2 Fermi energies. So this is a gain in the energy because of Cooper pairing. So we obtain very important result that the gap behaves exponentially as and inversely proportional to the product of the density of states and strength of the interaction. By the way, for those who look carefully at what I'm doing, can see that for exponent over 1 minus x is an essential point. So one cannot get these results by doing perturbation theory, because there is no perturbation theory if g goes to 0. This is essential point of your analytic function. The theory which I presented here is a sort of mean field theory and molecular field theory. We will come to more discussion of what this molecular or mean field theory means when we discuss magnetism, when we meet several types of the mean field theories, and we come to this discussion again. So, very important message which I got, that delta at temperature equal to 0 is equal to omega d e to the power 1 minus g. So you see the connection between solution of the Cooper pair problem and what I did today, but as I said, we didn't assume any pairing. We just assume that our ground state is unstable with respect to formation of the Cooper pairs. This is spontaneous breaking of the symmetry or second order phase transition. Let's do the same calculations at temperature equal to critical temperature. Actually, you can plug in this equation into your computer program, use Mathematica or use your Python programming and plot delta as a function of temperature. What you will get is this curve. So delta continuously going down and is equal to 0 precisely at the critical temperature. We defined and found what delta equal to 0 is. Now, if we define the critical temperature as a temperature where delta is equal to 0 in this equation, we will put delta is equal to 0 into the spectrum. 1 minus 2 mk is 1 minus 2 times e to the power ek over temperature plus 1. This is e to the epsilon k over temperature minus 1 divided by e to the epsilon k over temperature plus 1. This is e to the power ek over 2 temperature minus e to the power minus ek over 2 temperature divided by e epsilon k over 2 temperature plus e to the power minus ek over 2 temperature. So this is tangent hyperbolicus ek over 2 temperature. So therefore, the equation reads 1 is equal to V naught sigma prime. Here I have tangent hyperbolicus at Tc. As I said, gap is equal to 0, therefore epsilon k is equal to psi k. So this is psi k divided by 2 temperature divided by 2 psi k. This is how this equation looks at exactly critical temperature at this point. So now the right-hand side is equal to V naught 1/2 integral from minus omega d to omega d, density of state psi, tangent hyperbolicus psi over the temperature divided by psi, d psi. And again, I will replace the density of states by its value in the thermal energy. So this and another 1/2 comes because of the fixing spin projection. This is a density of states for full spin, and we are dealing with a given fixed projection of a spin. So this is V naught times 1/2. You remember I denoted as G as the Fermi energy, times 1/2. I replace integral from 0 to omega d, and have tangent hyperbolicus psi over 2 temperature, Tc. This is Tc, psi, xi. So what remains is to compute this integral. Of course, in order to do it, I first need to make it dimensionless. So I divide by 2 Tc and multiply by 2 Tc. Therefore, I have integral from 0 to omega d divided by 2 Tc, tangent hyperbolicus x divided by x dx. You will meet this sort of integral almost everywhere. Let's analyze how this function looks like. First of all, at x going to 0, this function doesn't diverge because tangent hyperbolicus is proportional to x. So there is no danger. If I now integrate it by part, so I have tangent hyperbolicus x times log x in the limit 0 omega d over 2 Tc minus integral from 0 to omega d log x dx divided by cosh hyperbolicus x squared. Now, you see that, sorry, omega d divided by 2 Tc. My intuition tells me that the critical temperature should be on the order of gap, and therefore it should be exponentially small for small interactions with respect to Debye frequency. Therefore, omega d over 2 Tc is very large, and this integral converges both in the lower limit and in the upper limit because of the exponent. So without losing generality, I can put this parameter equal to infinity. The first term at 0, it gives me 0 because x times log x is 0. At the upper limit, omega d is much larger than Tc, tangent hyperbolicus is equal to 1. So I have log omega d over 2 Tc. The second integral is just a number, minus log for gamma over pi, where gamma is so-called Euler constant. This is e to the power c. Sometimes c is called Euler constant. This is 1.78. So, what I got? That 1 over g is equal to log over 2 gamma omega d divided by p Tc, or Tc is equal to gamma over 2 pi, gamma over pi, sorry, 2 omega d e to the power minus 1 over g. So you see that my intuition was correct, that the critical temperature is of the order of the gap. Moreover, if I take twice gap at 0 temperature and divide it by Tc, I will get it equal to 2 pi divided by gamma. If you plug in the numbers, this is 3.5. This is universal number. So the ratio of a twice gap taken at a 0 temperature to the critical temperature is a number 3.5, and actually this is very nice benchmark of whether this electron-phonon interaction, whether the parent mechanism is related to electron-phonon interaction and you have BCS type theory or not. When the high temperature superconductivity was discovered in 1985, people measured gap. It can be measured by experiments, in particular the tunnel experiment. For measuring tunnel current gives you directly value of delta. You can take delta from thermodynamic measurements. You can measure delta through the Josephson effect. The measurement of 2 delta and ratio of 2 delta to TC showed the number which largely deviated from 3.5, which says that the mechanism of high temperature superconductivity was probably not related to electron-phone interaction, and moreover, the BCS theory probably not describing the high temperature superconductivity. However, all conventional superconductors, mercury, tungsten, aluminum, niobium, they all nicely fit by electron-phonon interaction and BCS theory. New high temperature superconductors like magnesium diboride is also electron-phonon superconductor, and this BCS theory was really breakthrough because it provides the explanation of the microscopic mechanism of superconductivity, and it gives the way how to compute the properties of superconductors microscopically. What you will do on a tutorial, you will analyze the solution of this equation, both in the temperatures close to to 0 and temperatures close to TC, and you will see, for example, that in the vicinity it indeed behaves as TC minus T divided by TC. So this is again a hallmark of a second order phase transition. Andrei will discuss it with you. Then, using this spectrum, you will compute the thermodynamics of a superconductor, and you will see that specific heat indeed has a jump at a critical temperature, as it should be for the second order phase transition, but at temperatures smaller compared to the gap, the specific heat behaves exponentially as exponent to the power minus delta over T, which is characteristic for all systems where spectrum is the gap. I want you once to see that whenever you find a gap in the spectrum, you can immediately say that contribution of these excitations to the thermodynamics at 0 temperature, at small temperatures, where temperatures are considered to be smaller compared to gap, is exponential. I want you to do this exercise. And then the last thing, Andrei will compute density of states for you. You can do this exercise yourself. I remind you before coming to the lecture. So the density of states, nu, n omega is integral over d p 2 pi q delta function omega minus p. So this is integral over dp over 2 pi q delta function omega minus square root of xi p squared plus delta squared. And you will find that the density of states is 0 for the frequencies smaller than gap. So it behaves like omega divided by square root over omega squared minus delta squared for omega smaller than delta. And it is 0 for omega, larger than delta. Sorry. And it is 0 for omega smaller than delta. However, I would like to remind you, whatever I'm saying about density of state, we have 3 variables. The density of states behaves as a square root. The critical temperature or delta or whatever is of the order of few kelvins. Even if it is room temperature, it is the Fermi energy. So we are affecting the density of states in the very narrow region because delta is much smaller compared to Fermi energy. And if I zoom in this, then I will get my n omega as square root diverging as a function of omega. So there are no states here. This is a gap, and there is 1 over square root divergence there. This is what you will compute with Andrei on Monday. And with this, we actually finish discussion of the superconductivity. I will come back to the summary of superconductivity on the very last lecture when we discuss ITC and behavior of strongly correlated system. But with 5 lectures and 2 exercises, I think it would be a nice introduction to this field. And for those who would like to learn more, I already recommended you a nice book of Schrieffer, one of the fathers of BCS theory, and also book of Abrikosov Theory of Metals, Fundamentals of Theory of Metals, where you can also find half book is devoted to the theory of superconductivity, including Ginsburg, Landau, and microscopic. Okay, any questions? I'm done.
Yeah.
Next Wednesday, we start with the magnetism.
I have a question.
Yes, please.
So the way that I know to get all these gap equation and everything, it's like you have your field theory, and then you decouple using a Hoover-Stratonovich transformation in the Cooper channel, and then you define your mean field, and that's the way that I know how you find it. I just want to make a parallel, like in here, it seems like the way that we find the gap equation and all these equations, it's by minimizing the Hamiltonian in the new ground state, right?
Well, there are plenty ways to derive these equations. In original work, Bardeen, Cooper, and Schrieffer constructed variation of wave function, and they showed that this variation of wave function leads to minimum of the free energy. This was original idea. Then, pretty soon, thanks to works of Bogolyubov and Landau, it was shown that this Bogolyubov transformation, which I used today, is very efficient tool to derive the BCS theory, minimizing energy as a functional by tuning this U and V coefficient to find out the minimum of the function. You can construct the quantum field theory, as you said, and introduce so-called anomalous averaging. This method using green functions is known as the Gaikov method. So these are Gaikov equations which allow you to derive the BCS equation in 2 lines. You need to deal with the Feynman diagrams and green functions. By the way, everything what I did here referred to so-called weak coupling. I assume that my coupling constant is pretty small, and both gap and critical temperature is much smaller compared to the bifrequency. If you have G very large, in principle, the theory which I present to you is not correct. In the strong coupling, large G, some other theory should be constructed by taking into account the retardation. This theory is known as theory of Eli-Ashberg equations, which take into account, as he said, retardation effect, that the processes are not momentary. So this is the 4th way to construct the theory. What you are referring, the path integral technique, where you indeed make a decoupling using Haber-Stratonovich transformation, and then you take a saddle point theorem to find out the saddle point of your path integral, and this is yet another way, but in order to justify the saddle point is the same level mean field theory, you need to again refer to weak coupling limit, because then the saddle point is deep enough, not shallow, and you're allowed to apply the descent path of descent method or saddle point solution. But basically, all this is very same, and this is matter of your many techniques you know, and what your preference. My preferred method is Markov equation. But in order to do it, you need to know green functions and Feynman diagrammatics. So you invest your time in learning diagrammatics, and then you can get many results in very short way. As I said, it will take me 6 lectures to teach you zero temperature green functions, final temperature green functions, and so on and so forth. And then in 10 minutes, I will derive BCS. So the same. I will need probably the same 6 lectures in order to define the properly path integral, define your coherent states, define your Grassmann variables which are needed to describe fermionic system, and the way people use these Grassmann variables, which are very counterintuitive, by the way. And then introduce you to the technique of path integral, and then, of course, many things can be done very quickly. Unfortunately, I'm using quite old-fashioned technique. I'm not denying that, but on the other hand, I don't need to teach you anything extra, but only those parts which you need for digesting of physics of this phenomenon. However, today I did a derivation without skipping any line. I started from the model and I derived the BCS equation and analyzed properties in one lecture.
I understand. Thanks.
Okay. Look,
okay. Yeah, Professor, if I understand right, you dedicate 6 lectures to teach us path integrals and green functions. Is this what you said?
Well, I would say I need 6 lectures for green functions and maybe another 6 lectures for path integral, because this is not the same. Of course, for the path integral, one can also use Feynman diagrammatics for analyzing diagrammatic series. You can invent diagrammatic for anything, for summation of your series, for computing the electric circuits, whatever you like. This is very powerful too. But I need 6 lectures both for the green functions and another 6 lectures for path integral in order to construct consistent basis and let's be familiar with the tools and exercises how to do it.
So I mean, we will do this, right? We'll do this in a later time, right?
No, I don't plan to do it. This is first of all very advanced course. I was teaching different courses in different universities of the world. In Germany, in France, in UK, I have my course of diagrammatic prepared. But you should also understand me. So if there is a request, say, in 5 or 6 persons, to have a sort of facultative course, I would consider seriously this request. But I'm not going to teach this course just for 1 person. And for 2 persons, the same. I would rather send you to self-education and provide you literature where to learn it. And this course goes far beyond the level of lectures which you used to have here. This is a methodological course. The course of many-body theory is actually aiming to discuss physics. Methodology is different. As I said, you invest some amount of time into learning method, and only then you will be facing some physics, some equations, which you derive in a more simple way. Here, this is not the aim of this course.
I see. I see.
So maybe those who will join the PhD program and those who are going to specialize in application of quantum field theory methods to statistical physics and solid state theory, they will probably have this course as a part of CISA PhD program on a PhD level. I can teach the phase transition theory using quantum field theoretical methods, which will be another at least 10 lectures. All beauties of Kosterlitz-Townless transition, of computing critical exponents, scaling. Yeah, but again, this is very advanced. I'm not sure that everybody will be interested in this, and I'm not sure that this knowledge, which is of course very important for any theorist working in modern condensed matter physics, but you know, now it's time of specialization. Some of you will be specializing in numerical physics and invest your time in something else. So that's the reality. I'm showing you the variety of interesting physics and interesting methods, and this is up to you to decide what you like more and what you would like to learn more deeply, so to say.
Also for the course machine learning with class students.
Yes, machine learning.
Yeah, I would like to join the that course with class students. Is it possible?
Yes, it is possible. It's yet undecided when it will take place. Most probably this machine learning course will be in May. So as soon as this course will be shaped, so to say, because this course is not offered by condensed matter and statistical physics section. It is offered by the section of quantitative life science. There will be a person from the staff of QLS teaching this course. This course will be mandatory for QLS students, so they will get credits for it. It will not be mandatory for the condensed matter students because we don't have any curriculum. So as soon as more information about this course will be available, I will let you know and will explain how to subscribe for this course.
So by the way, I want to ask if I also take the exam, whether it will be on the transcript.
I cannot give you any promise because we have mandatory curriculum, which is mandatory for everybody. You know, on one hand, I understand your request, and I'm very sympathetic to this request. On the other hand, we are opening Pandora box, which then each student would like to have his or her own curriculum and his or her own certificate, which is doable. I'm not saying that this is impossible, but it actually very strong perturbation to existing reality.
Yeah,
Maybe later we come to this modality, but I'm not sure we can do it immediately. But I remember your request. I will take it seriously.
Yes, thank you very much.
Okay, I see that there is a chat you are discussing among yourself, probably, right? But you should, I'm not saying no. As I said, if 5 persons would be ready to do it, and I also check your exam and homework, because 5 persons can volunteer, but if you perform badly on this exam, it will not make sense to do anything. Because you need to do excellent or very good in the mandatory course before you request some advanced course. And you should also understand that this is some work for the lecturer, for myself or anybody else who is doing that. In previous cases, my course was consisting of 16 lectures. Moreover, 4 of these lectures I presented with slides. This year, I'm presenting my course with 20 lectures, and only 2 of them are done with slides. So you see, you get 6 extra Blackboard lectures, which is almost increasing my Blackboard load by 50%. Partially it happens because Professor Nersisyan, who taught the course of many-body fundamentals, was not able to come this year. But you should also understand I would not be able to teach you like 40 lectures, 50 lectures, because I have my research, I have some other duties and responsibilities. Although I'm very positive to your request, but you should also understand other factors of reality. Besides, in March we start several other courses. This will be course of electronic structure calculations. There will be course of advanced statistical mechanics. There will be course of biological physics. So it's logistically necessary and important to find some slot such a way that you are not much loaded with your other duties, homeworks, exams. We need to plan it carefully. This is yet another problem. To be honest, but let you discuss it. You come to me with any suggestion, because I'm not actually saying that there are no any other things. There are plenty of interesting topics like topology physics and topology. Some numerical techniques like quantum Monte Carlo, because I want to balance analytical and numerical techniques. You know, physics is very interesting topic. This is why we all are here, and this is why we all are doing that. And all process of doing research is a process of constant learning. Yeah, and if you want to be professional theorist, you should be ready that you are going to learn all your professional life. Okay,